Okay, anyways, let's start for today. Okay, past two lessons, I'm going to do a quick recap on the one. Okay, then today we're just going to focus on the tutorial. Okay, so, wow, a lot of content here. But the first lesson content, I'm not really going to recap because the first lesson content is just like basic knowledge for organic chem. Okay, what I'm going to touch on is what we did on the second lesson. Okay, you can just write all this summary somewhere. Okay, it's a very short summary. Okay, but basically the first part of the last lesson, right, we went through hybridization. Okay, we discussed the rationale behind hybridization. Very quickly, let me go through the rationale. Okay, carbon has 6 electrons, more specifically, 4 valence electrons. Now, 4 valence electrons, that's why a lot of us think that carbon forms 4 bonds. Now, carbon does form 4 bonds, but the issue is that when you plot the electrons in an electron in box diagram, you'll realize one very interesting thing. It only has 2 unpaired electrons. And based on what we learned in atomic structure, having 2 unpaired electrons should only give you 2 bonds. So that's the problem that we aim to solve. Okay, we have 4 valence, somehow you can form 4 bonds, but we only have 2 unpaired electrons. So this is where hybridization comes in. That's where the S and the P orbitals start to combine with each other. Okay, but remember, there are 3 different shapes for carbon. Can you remember these 3 shapes? So this down these 3 shapes to do. Okay, that's tetrahedral. What else? Okay, trigonal planar, and finally, linear. Okay, so in other words, you should have a very good understanding of these 3 shapes. Okay, but we are focusing just on carbons. Okay, for tetrahedral shape, okay, definitely it's something that looks like this. Okay, can you remember what's the hybridization of tetrahedral carbons? Okay, good, sp3. Okay, so we call this sp3 hybridized, but more importantly, right, you need to remember the numbers. How many hybridized and how many unhybridized orbitals are there? So remember, this all dates back to your sigma and pi bonds. So look at this, how many sigma and how many pi bonds are there? Sorry? How many sigma? Okay, there are 4 sigma bonds, right? Okay, having 4 sigma bonds, how many pi bonds? Okay, no pi bonds, right? Okay, so if you have 4 sigma bonds, let's just recap a few important concepts. How do you form a sigma bond in general? How do the orbitals overlap? Okay, head-on. Okay, so that's number 1. You need to remember this. Okay, sigma bonds are formed via the head-on overlap of what kind of orbitals? Is it the hybridized orbitals that overlap head-on or the unhybridized orbitals? Okay, good. So it is the hybridized orbitals that overlap head-on to undergo head-on overlap to form a sigma bond. Okay, so that's number 1. Okay, and then of course, conversely, we have a pi bond. Pi bonds are formed via what? Okay, the sideway or side-on overlap of. Okay, good. Just your normal p orbitals, and these p orbitals are also known as unhybridized p orbitals because they just never participate in the combine. Okay, so once you remember these facts here, then you can count the number of respective orbitals that are. So considering that this guy is 4 sigma bonds, that means he will have how many? 4 which hybridized? Okay, we have 4 sp3 hybridized orbitals, and that's why this guy has no p orbitals. You can see that? So you just need to repeat the same process for the other 2 shapes. Okay, so for our trigonal planar shape, we have this thing here. Can we list down what's the hybridization first? Okay, sp2 and sigma pi, how many? 3 sigma and 1 pi. Okay, good. So let's list down how many. If there are 3 sigma bonds, that means that carbon has 3 sp2 hybridized orbitals. Good. And then finally, 1 pi means you have only 1 p orbital that doesn't participate in the hybridization, unhybridized. Okay. Finally, linear, usually you see this triple bond shape, but sometimes you might see carbon with 2 double bonds like that. Okay, this one you don't really see that much in your syllabus, but there's one question we'll do in the tutorial later that has to do with that. Okay, but either ways, both of them are linear. Okay, let's do the same thing again. What's the hybridization? Okay, sp followed by how many sigma, how many pi? Okay, just focus on this one. Okay, good. 2 sigma and then 2 pi over here. So if you have 2 sigma, you have 2 sp hybridized orbitals and 2 p orbitals. Okay, so you notice this is what you need to do yourself. Okay, you're not even required to memorize these numbers. Okay, you just have to list down the number of sigma and pi bonds. And remember these 2 facts, then you're safe. Okay, we also talk about one more thing under hybridization, which is the formation of bonds, okay, bond strength and bond length. Okay, so when we discuss bond strength and bond length, right, okay, let's just recall this small little portion here. How do we discuss bond strength? It's a very important factor. Bond strength is dependent on what? How effective the orbitals overlap. Okay, so always think of this term here. No matter where you go, right, in your entire chemistry syllabus, bond strength is you must tell me how effective, okay, the orbitals overlap with one another. The more effective the orbitals overlap, the stronger the bonds. Okay, that one should be quite obvious. Okay, but right, how effective the orbitals overlap can be dependent on two different factors. Okay, can tell me one of the factors that you have learned that's not really in hybridization. Okay, you all learned this like back in the day. Okay, let's just say we have HF versus HCl. How do you compare how effective the orbitals overlap? You look at the what? You look at the, okay, not really the electron count, but just the size. Okay, you have to look at the atomic size or the atomic radius. Okay, because the atomic radius is as such. The larger the atom, the more effective or less effective the orbitals overlap. Okay, if it's larger, right, it's actually less effective. Okay, remember that. Larger atoms overlap less effectively. Smaller atoms overlap more effectively. Okay, smaller is more compact. They can overlap a lot more with each other. Large are very bulky, very difficult to overlap with each other. You can see that? Okay, so that's for atomic radius. But then, right, sometimes right, when we compare different types of carbon atoms, perhaps something like this, okay, where we have different looking carbons everywhere, something like that. Okay, then this sounds a little bit different. You can't compare atomic radius because carbon all has the same size. That's where we have to discuss, remember, the percentage of S character. The more S character you have, the more effective the orbitals overlap. Okay, that's what we discussed last lesson. Okay, hands over. Okay, so that's the application of hybridization. You can use the hybridization of each orbital to discuss which orbitals overlap better. Okay? Okay, so that's for hybridization in a nutshell. Any questions? No? Okay, so we're gonna very quickly revise our isomerism now. Okay, but if okay, let's just start with the basics. Isomers, what's the definition of the isomer? You don't need to tell me the exact definition, but just tell me roughly what you do. Okay, just freestyle. Okay, what do you know about an isomer? Isomers are two things that have what? What's the similarity? What's the difference? Isomers have the same what, but different what. Okay. So we have two types of isomers. The first one is called structural isomers. A structural isomer is something that has the same molecular formula, but different structural formula. Okay, so you can have something like, let's say, C8H18. Okay, C8H18 is such a big compound. Okay, you can arrange this compound in so many different ways. So that's why you can get many, many different types of isomer. Okay, so that's called structural isomer. We've gone through three different types. Okay, that one's all in your notes. I'm not really focused on structural isomer. I just want to recap your stereoisomerism. Okay, this is the other type, other class of isomers that I want to talk about. Okay, the definition itself, okay, I don't really want to consider that, but can you just very, very quickly tell me what are the two types of isomers? Okay, sorry. Okay, good. We have cis-trans isomers, and then the other one is enantiomerism. Okay, so you should roughly know what is what already. Okay, your enantiomers are like your normal and mirror image. Your cis-trans is just cis versus trans, same type versus different sites. Okay, so very specifically, there's definitions and all that. Okay, but for summary, right? Okay, let's just go straight into the detail. Okay, can you just quickly tell me which is cis versus trans, just to get your mind moving. Okay, this one is what? Okay, cis. This one is trans. Okay, so I'm just gonna give you guys a few scenarios. This one, this double bond over here, can it undergo cis-trans? Okay, no, you see any double bond in a ring, okay, instantly out. Okay, unless it is 8 or more carbons, which you don't really see all that much. Okay, next scenario over here. Okay, first question, does this guy undergo cis-trans isomerism? Yes or no? Okay, remember the two different criteria. You must have a restricted bond, and then you have different groups on each side of the bond. Does it fulfill this? Different groups? Different groups. So it can undergo cis trans. Okay, I want you all to remember this. This one has 4 different groups. Okay, compared to the one that you see just now, this one you all can very quickly tell me which one is cis, which one is trans. Because you all can see, right, these two are the same groups on the same side. These two are the same groups on opposite sides. Okay, right? But the issue over here is that, why is it harder for you guys? Because there's nothing similar, right? All 4 are different groups. Okay, but you just need to know, this one I discussed the other lesson. Okay, this one can undergo cis trans. It's just that you do not need to know who is cis and who is trans. That's how it's can. Okay, so we have that. Okay, then also there's another final scenario over here. Okay, let's just say, right, I draw this compound for you guys. Can this guy over here undergo cis trans isomerism? I went through this exact scenario. Does it have a restricted bond? Okay, so a lot of you guys think that a restricted bond is a double bond, right? Okay, but remember, a double bond isn't just the only restricted bond. A ring is also considered a bond that is restricted in location. Because a ring itself is rigid, right? You cannot twist the ring. So you see, the double bond here is on opposite sides like this, over here and over here, right? But now the 2 different groups that we have to look at, right, is over here and over here. Can see that? Okay, so it's on opposite sides of the ring. You can see that, right? Okay, does each side of the ring have different groups? It actually is have, because you have one PR and also one H. Different groups. You have one BR and one H. Can you all see both ends of that restricted bond, which is the whole fat ring over there, has different groups. And that's why, right, cycloalkanes can also undergo cis trans, as long as each side you have different groups. They're different. It's the same principle over here for cis trans double bond. Different groups on each side of the restricted bond. Different groups on each side of the restricted bond. You can see that. Okay, so these are the scenarios that we have for cis trans. Later we practice some of the questions. Okay, okay, we look at enantiomerism. Okay, remember, in order to qualify as enantiomer, right, there are 2 criteria. Okay, I'll go through these 2 criteria, more important. What's the first criteria? The carbon must have what? Good. Okay, the carbon must be bonded to 4 different groups. Okay, so in order to have 4 different groups, right, guys? Just now remember the 3 different shapes that I talked about, right? Is it tetrahedral, trigonal, planar, or linear? Again, carbon only have these 3 shapes. So which one? Okay, good. In order to have 4 different groups, you must be a tetrahedral carbon. And this is something we're going to look at later. They will always ask you guys to spot for a chiral carbon. Okay, a carbon that has 4 different groups is called a chiral carbon. And a chiral carbon, right, must be tetrahedral. Just take note of that first. Okay, a chiral carbon that's not a tetrahedral carbon, you can pretty much ignore. Okay, so you slowly train to do this. Okay, the next thing is what? The molecule cannot be what? Good. Okay, the molecule cannot have any internal plane of symmetry. Okay, internally, if it's symmetrical, right, then you end up with this problem that I told you guys last lesson. Okay, remember, you have your mirror and then your hand. Your hand is an example of an image that's not superimposable. Okay, but then a symmetrical molecule, let's say this very symmetrical water bottle. Okay, the mirror image will be exactly the same, then you can overlap perfectly. Okay, that's why it cannot be symmetrical. Okay, can? Okay, other than that, okay, not much more for enantiomerism already. Okay, the rest is all about drawing of the mirror images, which we will discuss later. Okay, any questions? Okay, if there are no questions, right, we're just gonna go straight into our tutorial. Then we will see what all this means, right, on a level. Okay, so can you go over to question 4 first? Okay, last lesson we did question 2, okay, as a tutorial. Okay, but that one not very important. Okay, we look at question 4. Okay, we start with a little bit of hybridization first. Okay, I'll give you guys a bit of instruction on what to do. Okay. Okay, on question 4, there are 2 structures. I want you all to draw these 2 structures, and for each of the structure, you do the things at the bottom. Okay, they ask you to name the compound, hybridization, and geometry, and you explain the orbital overlaps, the sigma and pi bonds that we discussed just now. Okay, do one thing at a time first. I want you guys to draw the 2 structures, skeletal structure. Okay, skeletal for both A and B. Yeah, do that first. Okay. Yeah, the lines, the easiest, the most convenient way. Yes. Yeah. Oh no, it's for the questions later. The asterisk, they said, predict the hybridization and geometry of the carbon that has the asterisk. You can ignore it for now. You just take note of the first part here, I have two bromines, so we'll miss out. Okay, once you've drawn out the structures, okay, you can start naming the compounds. Remember, your naming rules, you must name from the right to the left. The most important thing is always from the right. And the most important thing is always a functional group. Okay? Identify the functional group first on the right, and then afterwards, slowly tell me what's the longest number of carbons in one. Okay, you mean to go through the naming? Okay, you're good. Okay, I'll go through the naming further, okay, because in a while, okay, but first of all, okay, you all look at this compound here, right? Can you all just tell me what's the main functional? Yeah, I know there's a bit of bromines over there. But after all, right, is it an alkane or alkene? We only learn these two. Okay, it's an alkane, right? Because there's only four single bonds. Okay, so you end up with something in. Okay, the next thing, what should we do? Should count the number of carbon atoms, right? Okay, the longest number of carbons over here is how many? Okay, four. Okay, four as well. Okay, good. So it's butane so far. Okay, but of course, after naming the 4 carbons, okay, we also need to number the position of the 4 carbons. Should we number 1, 2, 3, 4, left to right or what? Okay, good. Right to left, because all these little substituents are closer towards the right hand side. So that's why you should start numbering from the right hand side. Yeah? Okay, next. What's next? What should you do? How do you name the bromines? Bromine stands for bromo, right? Okay, how many bromines are there? 2. So it's called what? Dibromo. But at the same time, you need to number their position, right? So it should be what? 2 dibromo. It should be 2 dibromo. Okay, remember we mentioned also, right? The number of that substituent, right? You must repeat its position that number of times. So if there are 2 bromines, you need to repeat its position twice, regardless if it's the same number or not. So it's 2,2-dibromo, then butane. Can see that? Okay. How about that other name over there? The other one. How should we name this compound? Okay, what's the main functional group here? Okay, alkene. And how many carbons are there? 5. Okay. Then so it's what? Team. There's one more thing missing. You need to tell me the position of the double bond, right? So it is pent. Then what? Pent 2E. Yes. Okay, as you can see, the double bond is closer to the right hand side. So you start counting the bonds from the right hand side. I remember telling you guys also, here you count the bonds, you don't count the carbons. Okay, the bonds over here is the second bond. Okay, be very clear with that. Okay, so you go through the hybridization as well, okay, at the same time. Right, you take a look at this carbon with asterisk. What hybridization is this carbon? Okay, it is sp3 hybridized because, how do you know that? Okay, it's tetrahedral. So you can answer 2 things already. It is sp3 hybridized simply because it is a tetrahedrocarbon. 4 different groups, all 4 are single bonds. Okay. Before we go on to the other part, okay, there's one last thing they ask us to do, which is to indicate whether they are sigma or pi bonds and explain the orbital overlaps. So based on this carbon here, can you tell me the number of sigma and pi bonds? How many sigma and how many pi bonds are there? 5? No, just the carbon with the asterisk. Okay, just focus on him and then look at what's around it. Okay, there are just 4 sigma bonds, right? Okay, there are no pi bonds here. It's the same thing, but you don't even need to look at this. Just remember the tetrahedral shape. Okay, so you have 4 sigma bonds. So you tell me that the 4 sigma bonds are formed by the what? How is it formed? Okay, yes. So you tell me they are formed by the head-on overlap of, yes, okay, of S of 4 sp3 hybridized orbitals. You can specify the numbers. Okay, and you're done. Okay, I just need you all to do the same thing for fun, right? Soya bean with bone. You can try before. Is it hot? Soya bean is only hot. Yeah, same explanation as before, just a slightly different looking carbon, right? Okay, okay, I'm just gonna try to answer. Okay, so what hybridization and what's its geometry? Okay, sp2 because it is trigonoplanar. Okay, that's good enough. Okay, then we have how many sigma, how many pi bonds? 2 sigma, 1 pi? It should be 3 sigma and 1 pi. Okay, so we have a trigonoplanar carbon. I think you forgot to include the fact that there's an invisible hydrogen. Yeah, okay. There's an invisible H here. So remember that carbon must have 4 bonds. Don't always assume what you see on the skeletal formula is everything, because it probably won't be everything. Okay, there will be 4 bonds here. So you tell me 3 sigma, 1 pi. 3 sigma is formed via the head-on overlap of 3 sp2 hybridized orbitals. sp2, here's sp2 already. Okay, 1 pi is formed via the scion overlap of 1 p orbital. That's it. Finish. Okay, can? Hello? That's it. All good? Yeah, so that's hybridization. We'll talk more about that later, under with more questions. Okay, now I want you to look at the question on the next page. Okay, I drew up the structure already. Let me just show you guys. This structure looks crazy, I know. Okay, but just look at it very carefully. Okay, there are a few things that they want you guys to do. Okay, go and find the chiral carbons, and let's find the bonds that are formed via sp3 overlap. Okay, I know there's a few things here. Just look at the options first. The structure, I will help you out with it a little bit. Okay, first option, you're supposed to go and check whether there are 5 chiral carbons, whether there are 7 sp3 bonds. Do you remember? Go and check out. That one you need to look at each carbon's hybridization. And finally, whether their double bond can exhibit cis trans. Okay, why does the structure look like this? I'll show you guys first. Now, I know, right, you all don't know what a benzene ring looks like actually. Okay, so for now, I want you all to treat it as if a benzene ring looks like this. There are actually 3 double bonds inside this ring, alternating one another. Okay, so you can draw it at a side. Okay, so it looks something like that. Okay, and then this, you all see this little ring over here. You see the very bolded bonds, the black one. Yeah. Okay, that black one, right? I want you all to imagine the bonds are actually sticking out of the white. Okay, you can visualize the bit is like hanging out. Okay, the rest are like flat, right? And then the red color part is like sticking out of the, flopping out of the molecule, something like this. Okay, so try to imagine that those are still normal bonds. They just draw black, right? So that it is sticking out, so that you all can see a bit more clearly. Okay, they are still single bonds. Okay, then with that said, okay, go and look at the first option first. We do this one step at a time. Can you all go and find me 5 chiral carbons? Or if you can find more, that means the first statement is wrong. Okay, so you just go and check. Okay, I want you to number the chiral carbons. Okay, you find one, you put there 1. You find the second one, you put there 2, 3, 4, 5, 6, whatever. Okay, and just go and begin. Okay, or let me just give you some tips first, guys. For chiral carbons, okay, if you want to identify chiral carbons a bit more easily, right? Try to look out for shapes that look like this Y shape, or best is even this shape here. Now, of course, this is not the 4 groups. I'm just going over the shape. Generally, try to spot for this or spot for this. The more congested it is, right, the better. Okay, think of that. Because you want to ensure that there are at least 4 different groups. Okay, so these are good, and try to avoid these shapes. If you see a V shape as compared to this Y shape, this V shape will never come. Because why? There are 2 same hydrogens. You can see that. So you see a V shape, just look past it. Another one that you should avoid are anything that has double bonds. Because as we mentioned, guys, can a chiral carbon have a double bond? No, a chiral carbon needs to have 4 different groups. And 4 different groups is what shape? Tetrahedral. And tetrahedral will never have a double bond, right? Okay, that's just wrong. Okay, so you take a look at these guidelines, and then you try to spot over here. You see one, just put 1, see 2, just put 2. Okay. Again, I suggest you all draw the triple double bond for this benzene. Yep. It is different chemical. Okay. Yes, you start to realize that if you start to trace it outwards, it's like the rest of the molecule. Okay, but the moment is different, then you don't need to trace really. Okay, are you able to count 5 at least? Okay, I suggest you don't just, I know it's a very big molecule, but suggest, right, don't just start somewhere in the middle, then try to branch outwards. I suggest go with a flow, go from like up to down, down to up, left to right, whatever. At least there's a flow. Okay. Okay. Let me go through. Okay, come on, go through with you. Okay, actually, you don't need to keep tracing, keep tracing, keep tracing. Okay, we start at the top, then we slowly move towards the bottom. At least there's a flow. Okay, at the top over here. Okay, again, I'll try to spot for these shapes. I see one here. This is correct. So, okay, this carbon has a double bond. Okay, take note, guys. In other words, when you all see the benzene ring, the one with the ring in the middle, just ignore any carbons that are part of it. All these 1, 2, 3, 4, 5, 6 carbons in the benzene ring, never ever look at it because they all have double bonds, so they are irrelevant. Okay, so ignore this entire chunk ring. Okay, so I start to go downwards. Is this carbon chiral? No, it is the V shape. Instantly, it's out. Is this carbon chiral? Okay, it is this shape here, right? Kind of. Okay, you have minimally 3 bonds there, right? Okay, this is chiral because 1 is bonded to N, 2 and 3 are different. They are clearly different, right? Because you can see the molecule just branches off completely different ways, right? And finally, the last group is what? The last group is H, okay, invisible H. So usually I will say this one is quite likely to be chiral because one of these is already a H. Then the rest is like N, and these 2 carbons are definitely different ones. Okay, they go in completely different directions. So this is one. Okay, 1 chiral and N. Okay, we're just going to build on from here. Okay, the next guy is this guy chiral. Quite a high chance, right? Because he fulfills this shape over here. So you see, right, left, completely different directions really. Okay, then down also going towards the double bond, different direction, all three different groups. Okay, and then we have a H, so this is also definitely chiral. So you don't have to look at it so seriously, like, oh, if you really if it traces all the way back until it's the same. No, it will very unlikely be the same one. The only time when it's the same is when you go both sides, right? Then it is very symmetrical. But very clearly, this is not a symmetrical molecule. It's a very complicated molecule. You can see that. If we start to trace up, you want to go up or down? Okay, we go up here. Is this a chiral carbon? Does it fulfill one of these shapes? Yes, right. Okay, it's this shape here because it has at least 4. So that's a very high chance of getting correct. Because you already have 4 different groups. You can see that. And then you go up, you go left, you go right up. It's clearly different. You can see that. Okay, it will not be the same because you go up, there's one benzene ring. You go left, it's not a benzene ring already. Okay, it's different. You go to the right also, you completely see something else. Okay, so you go, then of course you go down here, this red color bond bonds to an N, so it's also different. So high chances. Right. Okay, and okay, we continue tracing. You must continue all this. If not, you don't just lose track. Okay, number 4. Is this chiral? Yes. Okay, it's not very obvious. You see one H, one O is 2 different groups. You go down, there's an OH. You go up, it's completely different. Okay, so this is 4. Okay, let's just go down. Okay, don't go up already. O is not carbon. We are not interested. Everything up there is done. Okay, we go down here. Is this a chiral set? Yes. Okay, you have this shape again. You have OH, carbon, double bond carbon, and then another H. This one definitely chiral. You can see that. Okay, so we already have 5. This one, anything? No. Okay, see double bond, ignore. You see a double bond, ignore. Are we done? Okay, let's just check our red color portion now. Our red color portion, this is a carbon. This is chiral. Okay, ignore all your V shapes. This one is it chiral? Ignore your V shape again. Okay, so far. Okay, so this one we done already. N is, I don't have an N. Is this chiral? Clearly not, so that's 3 of the same group. So the answer here is 5. Statement 1 is correct. Can see that? Okay, we'll practice seeing this now. You will definitely see this next time. Okay, you will have to look out for chiral centers. Okay, so again, it's to train you guys to see, to filter. Okay, I know for now you all look at it as everything is possible, but no. Once you filter out your double bonds, you filter out your shapes. It's a lot more. Okay, and okay, the next thing is, okay, let's do this together. Okay, we need to form sp3 overlaps. Okay, sp3 carbon. So I want you guys, let's find all the sp3 hybridized carbons. Okay, so far. Okay, I'll remove the 5 here. Let's just do our working for the second one. How do we find sp3 hybridized carbons? What's the easiest way to look out for sp3 carbon? How does it look like? sp3 is what shape again? Tetrahedral, and tetrahedral is usually seen with 4 sigma bonds, right? 4 single bonds. So try to find carbons that pretty much look like this, right? Ignore all your double bonds. Okay, they just want the sp3 carbons. Okay, so let's go from top to bottom again. Is this, okay, ignore all this, basically. All these are carbons with double bonds. You can see that. Okay, so gone already. I don't have an oxygen. Let's go to the right hand side. Okay, let's come here. Is this sp3 carbon? Yes. Okay, so it doesn't have to look like this. There are invisible H's also, and this one is definitely sp3 hybridized. You can see that? Okay. Now you go down here, is this sp3 hybridized? Yes, you see 3 single bonds already, but there's a 4th invisible one, so it's also sp3. Okay, let's go not down here because this is N. Let's go down here. Is this sp3? Tetrahedral. Yes, okay, you see 3 single bonds and also a H. Is this sp3? No. Is this sp3? Is this sp3? Is it? Okay, it is also. Okay, you can see very simple on all the single bonds. This one can? Yes, definitely also. Okay, so we find one loop already. Is that? Okay, yes also. Any more? Any more we need to consider? Did we miss out anything? Okay, this outer portion, the one that's sticking outwards. Okay, let's find all the other sp3 carbons. Is this sp3? Yes, yes also. Okay. Sun? Yes. You're not interested in N? Is this sp3? Yes. Okay, so they want sp3 overlapping with sp3. So that means the 2 carbons must be side by side, right? So now, right, the best way to showcase this, I want you to take out your highlighter. Go and highlight all the bonds that are formed via sp3 overlap. Okay, so I don't really have another color marker already. Okay, so I want you guys to highlight this in your answer. Okay, see whether, okay, just go and highlight yourself. All the sp3 bonds, highlight it out, see whether you got 7 highlights. Okay, if you don't have, that means wrong. Okay. Okay, how many have you all gotten? Okay, how many do you have? You're good. Okay. How many do you okay? 9. Okay. It is actually 7. Okay, there are 7. Okay, you see all the sp3 carbons here? Side by side. 1, 2, 3, 4, 5. But wait, there's 6, 7. Done. 7. You see that? Okay, so highlight these bonds out. Any you see as sp3 and sp3 side by side, you highlight that all. That's all we're doing. Okay. Okay, so let's answer our last question. The molecule cannot exhibit cis trans at the CC double bond. Okay, where's the CC double bond? It's like just right there. Okay, the benzene is not considered because it's drawn as a ring. Okay, so the double bond is here. Can it undergo cis trans? Yes or no? Can? Cannot? Cannot? No, answer is no. Why? Okay, you all notice the double bond, look at the bigger picture. What is it part of? Yes, it's part of a ring. You can see that. Okay, so the moment the double bond is in the ring, out already. Okay, that's the answer. Okay, so it is correct. So all 3 statements are correct. Okay. Okay, so this is one question done. Okay, once done with this, turn over to the next page. We are going to try question 6. Okay, in question 6, I want you all to just go straight to part C. Part A and part B are a bit waste of time to go through now. Okay, they ask you to define this and state the 2 types of stereoisomerism. That will do already. Okay, I'm just more interested in part C. Okay, can you all look at part C part 1? I want you all to kind of convert this right into a full skeletal formula first. Okay, and I want you all to tell me what type of stereoisomerism or what types it can exhibit. So is it cis trans? Is it enantiomerism? Or it can even be both. Okay, so go and specify. Okay, C part 1 first. Right? Specify the type of isomerism. Okay, draw out the skeletal formula of the thing as well. 1, 2, 3 carbons. Okay, count the number of carbons, so you can see. Okay, close enough, there's a bromine missing. Okay, just do part 1 first, because part we still have something else to draw, so you might need the space. Yeah. Okay. Okay, oh good. So it should look something like this. Okay, you want to switch it to the other side also, okay, something. Okay, so mainly, guys, you want to verify the number of carbons first. I know there's a lot of other things like double bond, bromine, right? Try to filter this out first. Okay, look at the carbons. I only count 3 carbons at the top, so that means you just draw out 3 carbons. Okay, then the first one is the one that's bonded to the PR. The first one meaning the one that's bonded to the ring. You can see that? Okay, so that's the first thing that we have. Okay. Yeah. Yes, supposed to be other side. Draw this again. Okay. Correct. Okay, so next, you need to tell me the type of stereoisomerisms that this guy can exhibit. Can it exhibit a cis trans? Okay, no. The double bond at the end can never exhibit cis trans. The one in the ring also cannot, right? So you check for the other one. Does it have chiral carbon for it to exhibit stereoisomerism? Have? Okay, have, where is the chiral center? How do we spot for the chiral center? Okay, try to find the Y shape. The first Y shape that I can see is here. Is this a chiral carbon? It is, right? Okay, this is a chiral center, so you might want to mark it out with an asterisk. Okay, any other chiral centers you can possibly see here, okay, just in case you miss out on it. Is this a chiral center? Is this a chiral center? It looks like a Y shape, right? But it's not, because you can see that this group and this group is the same. Because it's right smack in the middle of a symmetrical pentagon. You can see that? So you go down, right, and you go down here, they will link it up to they'll link up to the same point. So that's why it's the same group. Okay, so that's one chiral center. What they want us to do now is to draw the enantiomers. Okay, this is the enantiomer. We need to draw both its normal and its mirror image. Okay, so that means let's draw this guy out again. Okay, let's leave a bit of space. And we are going to specify, okay, we specify first, this is an enantiomerism. Once we specify this, I want you guys to draw the normal and mirror image. Okay, I'll show you how this is done first. Okay, remember, guys, if you want to draw a normal and mirror image, what formula must you use? Can you just draw like this? Are you able to just draw normal bonds? Okay, remember, when you want to draw enantiomers, you must draw the solid bond and the wedge bonds. Okay, so generally, I'll give you guys some tips here. The solid and wedge bond looks kind of like that. Okay, this is the one that we learned last lesson. But here, right, we are trying to convert it from a skeletal formula. So let's make things a bit easier for us. I want you to focus on this carbon here. The chiral carbon, you must convert it in this format. There are 2 bonds that are normal, and 2 bonds that need to change. I suggest the 2 bonds you need to change, these guys here, right, are the smallest atoms you can find on the molecule. Whereas the ones that are the normal bonds are these you don't want to change. So you should make it the biggest items on. So you look at this carbon in the middle here. Okay, should I change this bond down into a solid and wax bond? No, right? Because that one is too bulky, it's too big already. Can you tell me what are the two smallest atoms you can see on that asterisk carbon? There's also like H and a Br, right? So personally, what I would like to do is to just convert these two. Okay, then the rest, right, you just draw out as per normal first. So I draw these two out as per normal. Okay, something like that. Okay, can see that? Okay, then afterwards, I want you to convert it like this. Okay, so I have my Br, I converted it into a solid bond, and my H, I converted it into a dash. Here, then you can clearly see, right, I've drawn out my stereochemical formula. Can you see that? Then, of course, this is the normal image. I need to draw a mirror for my mirror image. Okay, how do you draw the mirror image here? Okay, I want you to go and try. Okay, let's fill out other diagram. Okay, then once you're done with this, right, okay, try to draw the skeletal formula for the next question also. Okay, and I suggest for the next question, count the carbons so you don't miss out on it. Fill out the mirror image. Okay, generally, the mirror image, right, you'll try to draw the normal bonds first, but I flip it to the other side. Okay, then you draw the solid and dash bonds at the end. Remember, whatever that's pointing outwards will still be pointing outwards. Whatever that's inwards will also same be pointing inwards. The bromine cannot be one pointing out, then the mirror is pointing in. A mirror must reflect exactly what you are doing. Okay. Now let's take a look at part 2. Okay, we're going to try to draw out the structure. Okay, again, I suggest you number the carbons to make things a bit easier. Okay, 6 carbons, all in a straight line here. As you can see, none of them are branching out. Okay, then from there, you start to edit each carbon. Right? Yeah. Sorry, the numbering is it? Okay, here, because we have a bit of conflict, the alkene is closer to the left, this alcohol is closer to the right. But we are not required to know which one is more important in that sense. Okay, but for your information, okay, the alkene will be more important than this alcohol here. So it's still named from left to right. Number from left to right. Okay, but we don't care about the naming for this. Okay, that one not required. Okay, okay, so for numbering, it doesn't matter. Here is just to ascertain that we have the correct number of carbons. Okay, but anyways, this is all you need to do here. 6 carbons, you just need to fill in your double bond and your OH. The double bond is in between 2 and 3, so 1, 2, 3. And then in between 5 and 6, carbon 5 is the one that's bonded to your OH. You see that? Okay, so let's specify what types of enantiomerism it can exhibit. Can it exhibit cis trans? Okay, there is a double bond there, right? Okay, does it have different groups on each carbon? Does it have different groups? Have also, right? Okay, this one H, one CH3. This one H and then one big chunk over here towards the right hand side. Okay, so definitely can exhibit cis trans. Okay, can it exhibit enantiomerism? Can it exhibit enantiomerism? Is there a chiral carbon anywhere? Try to spot the Y shape. We have a Y shape at the end here, right? And is this carbon chiral? It is. Okay, it is a chiral carbon because we have 4 different groups. So in other words, this molecule can exhibit both cis trans and enantiomerism. Now, even though the question never asked, right? Okay, let's just add in a few more additional items. Can you remember how to calculate the total number of stereoisomers that this guy can exhibit? Okay, go and write this down. Total number of stereoisomers. How do we calculate this? Okay, how to calculate this? Is there a formula? Okay, it is 2 to the power of something. Okay, it's 2 to the power of, okay, if you want to find the total number, because here can exhibit both cis trans and enantiomerism. What's the formula here? 2 to the power of M plus N, correct? Because M represents the number of double bonds that can undergo cis trans. N is the number of chiral carbons. So here was the answer. 2 to the power of 2, 1 each. So if you 4, we will have 4 total stereoisomers. And that's why for this part, we have to draw a little bit more. Okay, we have 4 different stereoisomers to draw. So what should we do here? How do we draw the 4 stereoisomers? Okay, think about it. This guy exhibits both cis trans and enantiomerism. Now let me just run through this with you guys. Okay, take note. Cis trans, there will be 1 cis and 1 trans, right? Enantiomerism, what are the isomers? The what and the what? The normal and the mirror image, right? So a lot of you guys will tell me this. You draw 1 cis, you draw 1 trans, you draw 1 normal image, and you draw 1 mirror image. Then I get 4 in total, correct? But this is wrong. Because I hope you all realize if you draw 1 cis, 1 trans, 1 normal, and 1 mirror, these 2 are not exhibiting at the same time. These 2 are happening on the same molecule at the same time, right? So that means you must exhibit both properties in the same isomer. So you can't just single-handedly go 1 cis, 1 trans. You can't make it separated like that. 1 normal, 1 mirror. You must have both effects at the same time. Okay, so this one you all haven't learned in math yet. So next time when you all see this, just remember one thing. I'll just tell you all the answer first. When you have cis trans and enantiomerism, these are the 4 combinations. The first one, okay, of course, right, we have 1 side mirror and 1 side normal, right? But we also have cis and trans. We can combine both together. Can you all tell me what's one possible combination? You must have one feature from each. You get the cis isomer that's on the normal image, right? That means on the other side is called what? Left side is a cis normal. Right side is the... Once you reflect in the mirror, it's called what? The cis mirror. Now we repeat the same thing. What's another configuration? I have 2 ready. I still need another 2 more. What are the 2 more? I have cis, so I have the trans as a normal image, and then I can also have trans as a mirror image. Can see that? Can see the difference with what we're trying to say just now. You are supposed to exhibit both properties in the same structure, in the same isomer. So both properties are present in each. So that's why you have 4 different combinations in total. Cis normal, cis mirror, trans normal, trans mirror. So we try to draw this up. Okay. Now if you look at the molecule that we drew just now, is this a cis or a trans? Currently, what you see here. Cis or trans? Okay, this is actually trans, right? Again, on opposite sides of the double bond. So let me draw the trans normal image first. I'll show you guys. Okay, so we have this trans. Okay, we just need to copy everything out except for this chiral carbon. You must change it to the solid and wedge bonds. Okay, so again, the smallest one, right? You try to convert it. So I have OH, right? So you see the OH now, I turn it into a solid bond over here. And then I also have an invisible H, so I convert it like this. So this is how you draw both cis trans and enantiomerism at the same time. It has come out before. Okay, so just take note of how this works. Okay, then how do you draw the mirror image? Just go and flip it around. I'm sure you all can do that yourself. And guys, how do you draw the cis version? This is the trans version. How do you draw the cis version? How do we just tweak this a little bit? How do we tweak this as easy as possible? Yeah, okay, just turn this, flip it upwards instead. Because once you flip it upwards, right, okay, as you can clearly see, this becomes a cis version, but the chiral center again never changed. Right? I'm just copying the same chiral center as before. So we have 2 different molecules, cis and trans, but both of these are the normal image. Do the same thing but for the mirror, just flip both so that that's how you can get 4 isomers in total. Okay, so I'll give you guys a bit of time to draw the mirror image. Okay, so a rather tricky question, but this is how you draw both cis trans and enantiomerism at the same time. Okay. Don't worry, they only ask you to draw 4. I know you can have like 8, 16, all the multiples of 2. Okay, but they never ask you guys to draw anything more than 4. You need to go a bit faster before we take a break. You don't need to write all this, but it's the I suggest you write. Okay, so that you all know what the 4 combinations are. Okay, you take one feature from each, then you just try to commute it. Okay, can? Okay, so very quickly, let's just draw this out. Remember, you flip it around that time, right? It should maintain the same integrity. Okay, that's your cis mirror. This is your trans mirror. Okay, so you just take the shorter side and then you just flip it. That's it. Okay? Okay, so that's how we draw some enantiomers, okay, and cis trans. Okay, I want you to now flip over to level up question 1. Okay, you need to go through this question, very important. Okay, this one we'll go through together. Okay, but perhaps right, I'll give you guys a bit of time to draw the structure first. Don't need to be skeletal. This one, no point draw skeletal. Okay, draw the normal thing first. Draw all the bonds. Okay, prompt 1, 2, die. Okay, just draw all this structure first. Okay, this one is a tricky question. Okay, so I'll just do it with you guys. Okay, but we need to go through all the 4 options, basically. Okay, there's a lot of space at the bottom. We're going to draw quite a few things. Okay, so make sure you leave a bit of space for that. Okay, but this is your prop 1, 2, die, and we are going to answer the 4 options. Okay, okay, I'll just look at the first option, right? Okay, this one is actually quite simple. Okay, just take a look. Okay, they're saying the double bond in prop 1, 2 diene is stronger than the double bond in ethene. Okay, so perhaps, right, let's draw out ethene as well. Okay, ethene is just 2 carbons, also has a double bond. Now, both of them are having double bonds. Okay, so how on earth are we supposed to compare the strength? What are we supposed to do, guys? Okay, we are talking about the bond strength, yes. So, but both are double bonds. So if they're all double bonds, shouldn't they have the same bond strength? Because look at the what? The bond strength is dependent on how effective the orbitals overlap. But in this case, how effective the orbitals overlap is dependent on what? Is it the atomic radius, the size? Okay, remember we went through 2 factors just now, right? It's dependent on what? Okay, is it dependent on atomic radius? Can we compare atomic radius over here? Okay, no, right? Because they are all carbon atoms. Okay, for carbon atoms, right, you can't compare size, so you must compare the percentage of S character. So for that, right, we need to identify the carbons hybridization. Agree? Okay, so let's identify everything here that we can see. Maybe we start first. What's the hybridization of these carbons? Okay, so this is an sp2-sp2 overlap. Okay, so you can take note of that. Okay, you must compare the hybridization first. Then you can see what orbitals are overlapping. Okay, this one, first carbon here is sp2, second carbon is sp. Yes, okay, third one is same as before, sp2. Okay, so when we look at a double bond here, it doesn't matter the left or the right. If you are looking at an sp2-sp overlap. Okay, so sp2-sp overlap versus an sp2-sp2 overlap. Which one has more S character? This one? Which one has a higher proportion of S? Okay, how many alphabets are there? There are S. There are 2 S out of how many alphabets in total? 2 out of 5, right? Then this one? 2 out of 6. Which one is more? This one. Okay, so this guy has a higher percentage of S character. Having a higher percentage of S character means what? Remember? Okay, the next point you need to write is more effective orbital overlap. And hence what? Hence, this carbon has a higher bond strength. Okay, this is something you are required to explain on. Okay, when you talk about the percentage of S character, okay, you are linking it towards effectiveness of orbital overlap. Okay, that's how you always explain bond strength factors. Okay, so the first statement is definitely correct, right? Okay, all good. We look at the second point now. Second option, you'll just tell me based on your first instinct, right? Is it correct or wrong? Rather interesting question here. They're saying the 2 pi bonds are perpendicular to each other. Can you just tell me where the pi bonds are first? Okay, for a carbon, linear carbon that looks like this, right? Okay, the pi bonds are over here, right? One here, one here. Let me just draw them in red. You can see that. Okay, we have 2 sigma and 2 pi. Those 2 pi bonds, they are sitting at perpendicular to each other. Does that make any sense? Okay, to you guys, it doesn't make any sense now. Okay, but I can tell you first that this statement is correct. The 2 pi bonds are indeed perpendicular to each other. How on earth does that happen? Okay, so that's when, right, I need you all to leave a bit of space to draw the diagram for the orbital overlaps. Okay, so let's draw the orbital overlaps here. Take a look. Okay, what's happening here is I need to draw all the orbital overlaps instead of drawing the bonds. Now, remember all your numbers that we learned just now. Okay, sp2, we got 3 sp2 and 1 p. sp, we got 2 sp and 2 p. Okay, we went through that just now already. Okay, so we just draw first. Okay, I want you to look at the double bond that's on the left hand side. Okay, we focus on one thing at a time. Okay, so let's draw the carbon. Okay, there's a third carbon on the right hand side. We don't care about that yet. Okay, let's settle all the bonds on the left carbon first. We have a sigma bond here, right? How's the sigma bond form? K-on overlap of what orbitals? sp2 and sp. These two guys overlap to form one sigma bond. So this is what you need to draw. One sp2 overlapping with one sp. Looking like that, let me draw it nicer. Okay, one sp2, one sp. Still looks like shit. Okay, but okay, this is your sigma bond. Okay, again, try to label everything. This is your sp hybridized orbital. This is your sp2. Wow, I can't get over this. It's too ugly. Again. Okay, this. What's wrong with drawing today? Getting a bit unsettled with this. Okay, so yes, okay, we have a sigma bond. We have, it's formed via sp2 and sp overlap. Okay, again, let's settle the other orbitals of this carbon. Okay. Yeah, let me just draw a little bit more after. Okay, you all take a look first. Okay, so on the left carbon, right, we have another 2 more sigma bonds, right? So these 2 sigma bonds are what? What orbitals? What orbitals we use for sigma bonds? sp2 also, right? Okay, so draw another 2 more sp2 in the shape of a trigonal planar. So this 1, this 2. Okay, again, we don't draw the orbital overlaps with H. We don't really care about that. Okay, but again, label these 2 are your sp2 hybridized orbitals. I'm sure you all can see, right? We have fulfilled 3 sp2 hybridized orbitals already. But we also have one more pi bond to fulfill. We still have one more p orbital to draw. And that pi bond is formed between these 2 carbons, right? So perhaps let's just draw the side one overlap of this. Okay, so draw one here, p orbital. Okay, and then this is another one. That's when you draw your orbital overlaps. Okay, overlap at the top and the bottom. And remember what I mentioned last lesson. You only want to label one of them. Don't label both. Okay, it's not 2 pi bonds. You must overlap both top and bottom just to form one pi bond. Okay? Label your p orbitals also. Right? Yeah. Alright. Okay, so we have to fulfill the same thing for the other side as well. You can clearly kind of see, right, that the other side is pretty much the same thing as this side over here. But let's just look at what's happening first. Okay, I want to focus on the sigma bond. The sigma bond here, right, same as before. This guy in the middle has sp hybridized carbon. This one is an sp2 hybridized carbon. They overlap, was labeled to form your sigma bond, right? Okay, so what I need you all to do here, this is your sp, this is your sp2. Do not label wrongly. Okay, the carbon in the middle only has 2 sp hybridized orbitals. Okay, then just repeat the same as before. Okay, trigonal planar carbons, okay, both sp2 as well. Okay, this is not really the concern. The concern is with the pi bond. Okay, you want to look at this first, can? Okay, we have another pi bond to fulfill on the right hand side. How should we draw this pi bond? Now don't copy this down yet, right? Okay, because it's wrong. A lot of you guys, right, will just tell me that, yeah, I can just do something like this one. And then I can just draw the exact same thing, and then this is my second pi bond. It looks perfectly fine, right? But this is wrong. Why is this wrong? Can you all focus on the carbon in the middle? The middle carbon is sp hybridized. How many sp hybridized orbitals must it have? How many? Okay, it has 2, right? But at the same time, it has how many p orbitals? 2. How many p orbitals have I drawn for this guy? I've only drawn 1, right? There's actually another p orbital you need to draw also. In other words, you can't borrow this p orbital and then use it to form another pi bond. It doesn't work that way. You have 1 p orbital, you can only form 1 pi bond. But apparently there's another pi bond, so that means I have to draw another p orbital, right? But take note, this second p orbital can be parallel to each other, side by side. No. As what we have drawn before, right? This p orbital has to be perpendicular. Something like this, okay, I know it's a little bit hard to draw here. Okay, so just imagine this now. It is perpendicular because, as we know, p orbitals exist only on 3 planes, x, y, and z. In this case, okay, we have perpendicular orbitals. So that's how you form your second pi bond. That's the only way out. Okay, the first one is this plane, the other one has to be a 90-degree angle. Okay, I know it's a little bit ugly here, okay, because you kind of have the sp2 orbital blockade. But that's not really the point. Okay, the point here is how I want to focus on the center carbon. I've drawn 2 sp and 2 p orbitals. And take note of this, I'll just go and explicitly write it down. The 2 p orbitals, right, on the sp hybridized carbon must be perpendicular to each other. And because they're perpendicular to each other, right, is the second statement now correct? The pi bonds are perpendicular to each other. Guys, you look at the diagram, right? Are the pi bonds perpendicular to each other? The first pi bond is here, the second pi bond is here. Are they perpendicular? They are. Can see that they are 90 degrees apart. This one is spacing like that, then the one is like, yeah, okay, so it is perpendicular to each other. Okay, initially it doesn't make any sense. Okay, but once you draw the orbital overlaps, you can clearly see. Okay, and how good with this? Okay, okay, look at part C now. Okay, can you tell me whether this is correct? This option C is very simple. Okay, correct. Okay, are there 2 sp hybridized carbons? Yes. Then that's answer. Is not the answer, but it's correct. Okay, 2 sp hybridized carbons, 1 sp hybridized carbon. That's it. Okay, can see. Yeah, okay, just count it. Yeah, okay, how about 4? Okay, you see, they ask you which one's not correct, right? The first 3 statements are correct. That means part option D must be incorrect. Now we look at this, they say that this compound is a planar molecule. Can you just look at this further? Okay, sp2 hybridized carbon is what shape? Trigonal planar. So it's trigonal planar. Yes, it's the word planar in this name, correct? Now, is linear a planar molecule, a planar shape? Okay, it is also a planar shape, right? Because it's just flat, 180 degrees, correct? Only your tetrahedral is known to be not planar, right? So what's going on over here? How come D is wrong? Then this planar is also planar one, right? Shouldn't the whole molecule be planar? Shouldn't it just be flat? But I hope you all realize this. Can you all see that the 2 pi bonds here are actually perpendicular to each other? So this molecule isn't just flat like this. If one side, I want you to imagine, the left side, right, the molecule looks like this. Okay, you just visualize this. But the right side, the molecule isn't like this also. It's actually like this. Can you see that? So you see my first finger, my thumb and my last finger. Imagine these two are your hydrogen atoms. 2 hydrogen, 2 hydrogen, and you can see that. Okay, and from here, you can see that initially it looks like this, so it looks planar. But because the other side is actually twisted at a 90-degree angle, right, you can see that it's no longer planar. You can see that? This is going in and out, this is going up and down. So how this molecule actually looks like, you all can draw the final shape of this. This molecule, one side is pointing up and pointing down, but the other side is pointing in and pointing out. You can see that this is how the molecule looks like because of the fact, right, that the two pi bonds were perpendicular to each other. So that means option B has led us to explain option B. This is a non-planar molecule. It's a tricky question, but again, I hope through this question you can understand your hybridization a bit better. Okay? All good with that? Yeah. Okay, so that's pretty much it for this question. Okay, we can take a short break first. Okay, later we can try the next question. Okay, all good. You look very tired. You wake up very early. Okay, so we talked about this last question. There are cis-trans isomerism or even enantiomerism when it comes to ring structure. So we discussed this. Okay, we have two different looking structures. They have their names over there, but let me just call them A and B, or X and Y. Okay, so this will be easier. Okay, so take a look. The first part of this question, they are saying that this compound exhibits cis-trans, and they want us to draw the cis-trans isomers. So they try. How should we draw the cis-trans isomers of a ring structure that doesn't contain double bonds? How would we do this? You remember just now, okay? How do we make it such that they are same sides of the ring or different sides of the ring? Now, this is no longer about double bonds. Double bond, very simple. Same side, just put it on the same side. Opposite side, just put opposite. But here, different. How? Okay, how do we show same side and opposite side? I mean, you can't bend like that and then bend the other way, right? But remember that this carbon is what shape? All these carbons here. Tetrahedral, right? Tetrahedral, we can draw a 3D structure, right? We can draw the solid and we can draw the wedge bonds. And that allows us, right, to do something that's on the same side on opposite sides. Can you see that? So let me give you an example first. They want us to draw the cis isomer. How do we draw the cis isomer? How do we change the PR atoms? They should be pointing to the same plane, right? So you look at this. If it is the cis isomer, you can make the PR, the wedge bond, this PR, also a wedge bond. Can you see that? Okay. Whereas on the other hand, the dash bond is what? H. And this dash bond is also H. In other words, the bottom line is a cis isomer has to be on the same side. But this is a ring, so it has to be the same side of the ring. So I want to imagine this. I want you to perhaps look at it from another perspective. Imagine this ring step like this, not facing up, down, it's facing flat like that. Can you see on this flat ring? Imagine this iPad here is my ring, and then right, the two bromine atoms are pointing outwards, right? So that means you have two bromine atoms that are pointing out like that. So that's on the same side. Can you see that? Does that make sense? Can visualize? Right now, because the ring is facing you guys, right? So it looks like this. The two bromines are like two markers, and then it's facing towards you guys. You can see that? Okay, is there another version of a cis isomer? I can also draw both bromine atoms as dash bonds, right? So that they are both facing inwards now. So now it's looking like that from your perspective. You see that? Yeah. Yeah, you must imagine it as sticking towards you, pointing towards you. It's not going up. I know because it's a 2D whiteboard. Okay, but this ring, just imagine it as a flat piece of paper. Now currently it's like that. So your bromine is sticking out like that, sticking out like this. But if you want it to be on the same side, cis, you can also put both bromine atoms as facing inwards. So I will show the other version also. As long as they are pointing on the same side, that's safe. So bromine pointing inwards, bromine pointing inwards. This is also correct. Point into the whiteboard, away from it. Correct. That's how you read this notation. Okay, this is another version of the cis isomer. But right now, you just need to make sure that your H's are pointing outwards. So this is how you draw cis-trans, right, for ring structures. Does that make sense? It's all about pointing same side or opposite sides. The ring is a restricted point. You cannot rotate a ring. That's why this guy can exhibit cis-trans. Both ends of the ring have different roots. Does that make sense? So guys, how will you draw the trans isomer? Give it a try. Okay, give the trans isomer a try. Okay, trans just means opposite. So you can play around with the bonds, the positioning. Okay, these two are possible answers. You can draw any one of them. Okay, and this. Okay, so trans just means the bromines are now on opposite sides of the ring, opposite planes. So if the first bromine, right, made it a solid bond like this, that means the other bromine must be what? Dash bond. Now you can see, this is how it looks like. Your flat piece of paper, you have one bromine sticking out and one bromine sticking in. So imagine the ring is now flat, right? This is how it would look like. The ring now facing towards you guys, so this is how it looks like from this perspective. Okay, so that's same side versus opposite sides. You want to draw in the H's, you can. Okay, you notice this is also an acceptable answer. You don't need to draw the H's because number one, a bit congested. And number two, H's are already meant to be visible. So H's you want to ignore also can. So let me just ignore the H's for it now. So this one looks a bit easier to see. Okay, then. Okay, we're going to go over the second part. And the second part, right, I don't want you all to just read the second part because let me just go through from the board over here. Okay, I want to talk about a few things. Okay, before we talk about part 2 properly. Okay, now you notice this structure X that we just discussed. They said this guy can undergo cis-trans isomerism. The second question I want to ask you guys is, can this guy undergo enantiomerism? Okay, they never say whether can or cannot. So can this guy undergo enantiomerism? Does it have a chiral center? Can find all the Y shapes again. Okay. This is a Y shape, right? Is this a chiral center? No, it's not. Okay, good. Because as you can see, they both trace to the same position. So there are no chiral centers of X. It cannot undergo cis-trans. Sorry, it cannot undergo enantiomerism. It can only undergo cis-trans. Okay, good thing of this. No enantiomerism because no chiral center. Okay. Now, we are going to move on to compound 1. And we're going to identify first. Can this guy undergo cis-trans and can this guy undergo enantiomerism? Okay, so let's check first. Can this guy undergo cis-trans? Can it exhibit the same thing as before? Can I put the bromines on opposite sides or the same sides? Okay, first of all, is there a restricted bond? There is, right? Okay, now it's not completely directly opposite. Okay, so perhaps you can twist this a little bit, right? Such that it looks like that. Can see that? Again, I move it a little bit up. Can see that you have opposite sides of the ring. A restricted bond. And you have two different groups also, H and PR, H and PR, can see that? So yes, you can have cis-trans isomerism for this guy also. You have a restricted bond and you have different groups on each side of the restricted bond. Okay? But what I'm more interested in is enantiomerism. Is there a chiral center in this molecule? Find the Y shape first. This Y shape here, does it have a chiral center? Is it chiral? Answer here is yes. Now why? Take a look. Bromine is one group, hydrogen is another group, right? Okay, I have two different already. Now you check the left and the right hand side. Are they the same thing? You trace the left, you end up here. You trace the right, you also end up here. But are they really the same? They are not the same, right? Because the right hand side also have an extra PR. So clearly the left and the right, even though they end up at the same spot, right? It's very clear that the right hand side is different from the left. So it is different groups. You see, the moment you change the position of the PR, you already get a different looking structure. Okay, so there is a chiral center in the structure Y. So conversely, I find another similar looking carbon. Is this chiral also? Okay, it's the same exact carbon, right? Just on the other side only. Okay, so this guy is chiral as well. We have two chiral carbons. Okay, so the next question is this. Y'all follow me through this. Can he exhibit enantiomerism? Other than having chiral centers, what's the other criteria you also need to fulfill? No symmetry. Is there any symmetry in this molecule? Have or no? Okay. You notice there is a way to cut the molecule into two equal pieces. So by doing this way, this is actually a symmetrical molecule, right? Okay, now, before the symmetry came into place, right? Okay, I can tell you this. Can this guy undergo enantiomerism? We don't really have a concrete answer for that yet. Okay, you'll see why. Okay, so he has two chiral centers. What's the total number of steroid? What's the total number of enantiomers you can expect to get? Okay, I'm only focused on this guy, enantiomers. How many enantiomers can you get here? I'm not concerned with cis-trans. If you have two chiral centers, so it's 2 to the power of 2. You should get 4 enantiomers in total, right? Right? But because there is an internal plane of symmetry, okay, the total number of enantiomers, right, actually are only 3. So if you look at part 2 now, this guy has 2 chiral carbons, and it will give rise to 3 stereoisomers, which is what we just talked about. Now, you don't really need to know how this 3 came about, but it's basically just 4 minus 1. Why is there a minus 1? Because only 2 out of the 3 are optically active. Okay, we will see how this works out. Okay, this part you don't really need to copy. Okay, we expected to see 4, but in fact, there's only 3. And I want you guys to draw all 3 out. I know they only ask you guys to draw the structure of the optically inactive stereoisomer. Let's draw all 3. So take a look at this, guys. On first glance, this one isn't symmetrical, right? So on first glance, this is symmetrical. So by right, it shouldn't exhibit enantiomerism. But it actually can. Why? You look at these carbons. Again, these carbons, is the bromine just flat like that? As we went through just now, the bromine is actually the carbon is tetrahedral, right? So the bromine can either point out or point in. So we realize something like this. We can actually change these bonds here, right? And to make it symmetrical, okay, you take a look first, right? There is a way that I can make this compound not symmetrical. What should I do? What should I do to the bromines to make this compound not symmetrical? One bromine, if it points outwards, what should the other bromine be such that the molecule is not symmetrical? Inwards. Good. Can you draw a line comfortably cutting this into 2? No, because this is not symmetrical anymore. They are on different planes. So take note, when the bromines are on different planes, the molecule is not symmetrical. And if it's not symmetrical, plus the fact that it has chiral carbons, Okay, this guy can undergo enantiomerism. In other words, he's optically active. He can rotate plane polarized light because he can exhibit enantiomerism. Can see that? Two chiral centers, yet there's no symmetry, so you would have this guy can be optically active. Can you see that? Okay. Now, this is the normal image. We have drawn one out of the three. Okay, they said there's three, right? We've drawn one, right? If this is the normal image, that means we need to draw its mirror image. The mirror of this compound will be optically active also. So you see, dash will still be dash. Solid will still be solid. So these two guys are optically active. This is just the mirror image of the first one. Okay, this is the normal. This is the mirror. Also optically active. So you see the question here. It fits the question. 3 stereoisomers. Only 2 are optically active. These are the 2. You can see that. Then which one is the not optically active one? Same side. Can see that? Good. Okay, let's repeat the same thing. Why is it that same side is not optically active? Okay, guys, why is it that same side is not optically active? If the bromines are on the same side, so if this is solid, this is also solid, right? Why is this not optically active? It's still the same chiral centers, but why is it cannot rotate plane polarized light? When they are on the same side, then this is symmetrical. Exactly. That's why we have 3 stereoisomers in total, but only 2 of which, the normal and mirror of that, okay, then it is, right, optically active. Okay, so you take a look. This is the trans isomer. The trans normal and the trans mirror are optically active. Now, remember the combinations that we did just now? Trans normal, trans mirror. Then we have what? Cis normal, cis mirror. Trans normal, trans mirror, both of them optically active. You can see that. But then, of course, this is the cis. Now, there's no cis normal or cis mirror. There's no normal mirror in the first place because this guy has internal plane of symmetry. So it's not optically active in the first place. So there's no mirror. It's just cis. So that's like 1, 2, 3. So in other words, I'm going to give an explanation for this. Okay? When they are on the same planes, they are, okay, there's an internal plane of symmetry. And as a result, not optically active. So we have yet again combine the cis and the trans idea together. Slightly challenging question, I know. Okay. But I need to show you guys how. Okay. The first time you all see this molecule, let me just repeat as you all are doing. First time you all see this molecule, it is symmetrical. Then it looks very symmetrical, right? But actually, if you just go and play around with the planes, you're going to make them on different planes only, then they're not symmetrical already. That's it. Can see that? Okay, I'll say it again. Okay. You can make it not symmetrical by putting them on different planes. Then become optically active. But if you don't want to be optically active, then put them on the same plane. Same plane will be symmetrical. Different plane, not symmetrical. That's good. Okay. They have tested this quite recently in the few J2 exams. Here's how to focus on this a bit more. Okay. It's all about. Don't just look at it from the first glance.